Hello everyone, welcome back to Academics TT. In this video we will be looking at the second part of complex numbers, which is all about the Moivres theorem and loci in the complex plane. If you haven't watched the first video, I suggest you go back and do that quickly. That way you will properly understand exactly what is going on in this video. So the Moivres theorem is something that completely changed complex numbers and has a lot of different applications, which we're going to look at shortly. Put simply, it states that cosine of theta plus I sine of theta raised to the power of n is equivalent to cosine of n theta plus I sine of n theta. So the first application of de Moivre's theorem is raising a complex number to a power. So let's suppose that we have the complex number root 3 plus I all to the power of 8. Now, expanding this as we usually would take way too much time, so we can use de Moivre's theorem as a sort of shortcut. Firstly, you have to convert it into polar form, and you should remember from the previous video, to convert to polar form you first have to find its argument, theta, and distance, or modulus, from the origin. So for I plus root 3, the argument will be the tan inverse of 1 over root 3, which is pi on 6. And to find r, we can use Pythagoras' theorem, which says that r is the root of root 3 squared plus 1 squared, which is the root of 4, which is 2. So I plus root 3 is, if we let that equal z, is equal to 2 cosine of pi on 6 plus 2i sine of pi on 6. So now that we have this, we can do what we did with the Moivre's theorem and just pull the 8 inside the cosine and inside the sine. So it will become cosine of 8 pi on 6 plus I sine of 8 pi on 6. Don't forget that this 2 is also being raised to the power of 8. So it has to be taken care of on the outside. Now this is equivalent to this. All you need to do is put this in your calculator and it'll solve it for you. Simply, you don't need to go and try to solve this by yourself. So there we go. Because we had de Moivre's theorem, we were able to change this to this in just a few simple steps. Now, before we go any further to more of the applications of de Moivre's theorem, we have to familiarize ourselves with a tool that is used in complex numbers called Pascal's Triangle. Now, Pascal's Triangle, if you just focus on this for a moment, is constructed as follows. So you start off with a 1 on the top, and essentially you add every number that is on top, or you add the 2 numbers that are on top of it to get the number below. So for example, 1, you can imagine a 0 is here, so you get a 1 here, and another 0 here, so you get another 1. A 1 plus 1 gives a 2. And the same process can be used to give you 1s on all sides of the triangle. Now for this row, 1 plus 2 is 3, 2 plus 1 is also 3. So you get 1, 3, 3, 1. And for this row, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4 again. You'll notice that Pascal's triangle is symmetrical about the middle. And you can continue this for any number, really. But what it's useful for is finding out the coefficients when you expand a binomial like this. So for example, if I have a plus b to the power of 0, that is n is 0, we know that the coefficients will be, of course, 1. If n equals 1, the coefficients will be this. And for example, let's say this was a quadratic, we squared this, we know that we would have a squared plus 2ab plus b squared. So this represents the coefficients when you expand this, and it starts off at n equals 0, and I have drawn up to n equals 5. And don't worry, usually you don't need to go past n equals 6. So now that we understand Pascal's triangle, we can move on to the second application of de Moivre's theorem, which is expressing multiple angle trigs in powers. So for example, if you had to represent tan of 6 theta in powers, that would be, for example, let's say 3 tan squared plus 4 tan cubed plus 5 tan to the power of 7, who knows? We need to find out what it is in terms of powers. Now to do this, the first step is you look at the argument and you write cosine of 6 theta plus I sine of 6 theta. And this would have to be the same argument as whatever trig you're looking for. Now, because of the Moivres theorem, we know that this is equal to this. This is equivalent to this. All we did was pull the 6 out of the powers and outside these brackets. So what does that tell us? Well, if we expand this here, we will know that the real part of this is equal to cosine of 6 theta, and the imaginary part of this expansion will be equal to I sine of 6 theta. And well, if we have cosine of 6 theta and I sine of 6 theta, we can obviously find tan of 6 theta. So the first thing we do is we find out what the coefficients are going to be once we expand this to the power of 6. So from Pascal's triangle, we know that if n equals 6, well, firstly, we're going to have a 1 on this side, and we're going to have 6, then 5 plus 10 gives 15, 20, and we know it's going to be symmetrical, so we go back to 15, 6, and then 1 again. So these will be the coefficients when we raise a binomial to the power of 6. So we have the coefficients as 1, 6, 15, 20, 15, 6, and 1. The next step is as follows. So you're going to take cosine of theta and you're going to raise it to the power of 6. And you're going to give it you're going to give that the first coefficient. Next, you're going to take cosine of theta and raise it to 1 less power. But this time you're going to include I sine of theta. So the next term in this expansion will be 6 cosine to the power of 5 theta by I sine of theta. And you continue that pattern by dropping the power of cosine theta by 1 and increasing this power by 1, while also keeping in mind that they must have these coefficients. If you do that, you should get something that looks like this. So we have cosine of 6 theta, we drop the power to cosine 5, coefficient is 6, I sine of theta. Next we have 15 cosine to the power of 4 theta, and don't forget you're squaring this whole thing, so it should be I squared sine squared theta. The next coefficient is 20, and you do the same thing. You drop the power, increase the power of this by 1, and you end up with this entire expression here as the expansion of this. So now that we've done that, what does that tell us? Well, if we find the real part of this, that will be equal to cosine of 6 theta. And if we find the imaginary part, that will be equal to I sine of 6 theta. So the real part will be everything in this without I. Keep in mind that even powers of I are real and odd powers of I are not real, because I cubed is minus I, and I to the 4th is just 1, and I squared is minus 1. So we know that cosine to the power of 6 theta is real. We also know that this is real, because this is minus 15 cos to the 4 theta sine squared theta. We know that this is also real, and we know that this is real here, which means that this, and this are the imaginary parts. So we know that cosine of 6 theta is equal to this plus this plus this plus this, and we know that I sine of 6 theta is equal to this plus this plus this. Now, what does that tell us? So we can rewrite cosine of 6 theta out here like this, and sine of 6 theta, all you do is you get rid of the i's. So you had I sine of 6 theta originally, you got rid of the I on that side, so you had to get rid of the I in each of these terms. So tan of 6 theta is just going to be sine of 6 theta divided by cosine of 6 theta. And once you do that, you should end up with this. So we have now 6 cosine to the 5 theta, sine theta, minus, and you have all of this. So you could stop here, but if they asked you for tan of 6 theta all in terms of tan theta, what would you do? Well, at this point, you divide by the highest power of cosine in this whole fraction. So the highest power of cosine is 6. So we have to divide top and bottom, so the value of the fraction doesn't change, by cosine to the power of 6 theta. So what does that give you? Well, this term becomes 6 tan theta. This term becomes minus 20 tan cubed theta. This term becomes 6 tan fifth theta. This term becomes 1. This term becomes minus 15 tan squared theta. This term becomes positive 15 tan to the 4 theta. And this term becomes just tan 6 theta by itself. So you divide it by the highest power of cosine, and you end up with this. So if they had just asked for cosine of 6 theta or sine of 6 theta, you could have stopped here and just isolated these to get your answer. So now we can also use the Moivres theorem to do the reverse process. We can go from a power of a trig to a multiple angle of a trig. And to do that, we need to introduce another tool, a sort of made-up theorem. So if we know that z is equal to cosine of theta plus I sine of theta, and we know that z to the n is equal to cosine of n theta plus I sine of n theta from the Moivres theorem. Now we can manipulate this to find out something interesting. What happens if we have 1 over z to the n? Well, that will just be 1 over this. And if we multiply by the conjugate of this to realize the denominator, to make the bottom of this real, similar to surds, this is what we end up with. We end up with cosine of n theta minus I sine of n theta. Because you'll see that once you multiply out the bottom, you end up with cos squared n theta plus sine squared n theta, which is just 1. And you're left with this top here. So we know that 1 over z to the n is equal to this. So that tells us two things now. We know that z to the n plus 1 over z to the n, which is this plus this, is going to give you 2 cosine of n theta. And we know that z to the n minus 1 over z to the n, which is this minus this, is going to get you 2I sine of n theta. So let's use what we've just learned. So let's suppose we have to convert this to multiple angles. So the first thing that you do is you start off with, well, if this was sine, you would have started off with 2I sine theta, but because it's cosine, you start off with 2 cosine of theta. Now, from the rule before, we know that 2 cosine of n theta is equal to z to the n plus 1 over z to the n. So if n is 1, 2 cosine of theta is just equal to z plus 1 over z. So now, whatever this power is, you raise both sides of the equation to that same power. So because we want to find cosine to the power of 4 theta, we raise both sides to the power of 4. So this becomes 2 to the 4 by cosine to the power of 4 theta is equal to z plus 1 over z all to the power of 4. Now this is also a binomial, so we need to reintroduce Pascal's triangle, which will tell us that the coefficients of this expansion will be 1, 4, 6, 4, and 1. So we can repeat the process that we did before and expand this. So we end up with 1 z to the 4, then we have 4, remember you drop the power, z cubed, and then you introduce this, multiplied by 1 over z, and then you have 6 z squared, drop the power again, increase this power by 1, by 1 over z squared, plus 4 by z by 1 over z cubed, and then you have 1 by 1 over z to the power of 4. Now what we can do is we can group like terms. So z to the 4 plus 1 over z to the 4, we can group them together. And we can group 4, this ends up being z squared, and this ends up being 1 over z squared. So we can group 4 by z squared plus 1 over z squared, and then, well, the z squareds can't cancel with the 1 over z squared here, so this just leaves you with 6. So this, when expanded, is equal to this. Now, we know that z to the n plus 1 over z to the n is equal to 2 cosine of n theta. So we can do a reverse substitution and say that this term here is equal to 2 cosine of 4 theta. This term is equal to 2 by 4 by cosine of 2 theta, and well, this 6 just remains the same. So you end up with this on this side. But don't forget, over on this side, you also raise 2 to the power of 4. So we have 16 by cosine to the 4 theta is equal to this whole thing here. So if you want to get cosine to the 4 theta, you just divide both sides by 16 and you will get your answer. So those are all the applications of the Moivres theorem that students need to know. The next part we'll be looking at is loci in the complex plane. So that is essentially shapes and lines and different things that you can do with complex numbers within the complex plane. So if we take a look at this form of equation here, we have z, a complex number, minus a constant is equal to r, another constant. So what do these two lines mean? This means the distance of z from C. So what this represents, well, let's think about it. This is telling us that the distance of a complex number from a point will be constant. What does that remind us of? Well, that would be a circle, because the distance of z from the center C will be a constant distance r, which we can represent as the radius. So let's suppose we have the complex number z plus z minus, the mod of z minus 1 plus I is equal to 4. That is a circle of center 1 plus I with radius 4. So 1 plus I is about here in the complex plane, and we know that the radius will be about 4, and it'll be a circle like that. So this will be the center. So if we were to represent that, it would be something like this. So you'd have a circle. This represents all values z can take, the orange line, and well, this is just the center 1 plus I, and the radius will be 4. So that is the first form of loci in the complex plane. So the second form of loci is something like this. It seems a little bit confusing, but it's not really. So this tells us that the argument of z in relation to a complex number is equal to a specific angle. Now what might this tell us? Well, this is a half line. You'll see what I mean by half line soon. Starting at the point A, inclined at an angle of alpha upwards from the real axis. So for example, if we have this here, the argument of z minus 2 is equal to pi over 4. Well, the half line starts at the point 2, and it is inclined upwards at an angle of pi over 4. So what does that look like? It looks like something like this. So it's called a half line because it only starts at a point and goes onwards. Everything underneath is not allowed to be shown on this line. So this represents all possible values z can take, given that it fulfills this equation here. So every value of z will lie on this half line. So the last form of loci in the complex plane is this. Now this tells us, remember, modulus represents distance of z from this point here. So the mod of z minus a equals the mod of z minus b. So that tells us that the distance of z from one point must be the same as the distance of z from another point. So let's put that into context to figure out what this might actually be. Let's suppose you have it represented like this. So we have the distance of z from 1 plus I is equal to the distance of z from 3 plus I. So if we take a look at where these 2 points lie on the complex plane, 1 plus I is about here, and 3 plus I is about here. So these 2 points, so where's z? Well, those are these 2 points here. Now we know that the distance of z from these 2 points is the same. So what that tells us is that z can only exist along a line that is halfway in between these 2 points. So what it is the perpendicular bisector of the line joining the 2 points specified in the equation. So it'll look something like this. Z can only lie along this line because it'll be equidistant from this point and this point. One important thing to note is that you shouldn't confuse these two with each other. So in the first case, you have mod of z minus a equals mod of z minus b. In this case, you keep this side, but on one side, you are multiplying this by a constant k. Now what this does is this sort of changes this line into a circle. So this represents a circle in the complex plane. Usually not much manipulation is required of students in CAPE. I've never seen it come in a question before, but it is just an important point to note. So before I close off, let's just take a quick look at what happens when you introduce inequalities into loci. So this is the original circle that we had. I'm going to put that aside for a moment. So let's suppose instead of z minus 1 plus I is equal to 4, let's suppose they said less than 4. What would that represent? Well, if you had to represent that on a diagram, you would still draw the same circle represented by this equation, but instead, because it has to be less than 4, it'll be everything inside of the circle. So you would have to shade it if you got this in a test or a quiz to represent less than. And if it instead it was greater than, you'd have to shade everything outside the circle. Similarly, with the argument, you're going to have a half line like this. If this was less than pi on 4, you'd have to shade everything under here. And if it was greater than pi on 4, you'd have to shade everything here. Because remember, the argument goes all the way up to pi on this side, and then it comes around negative to close to minus pi on this side. So if it's less than, you shade everything under. If it's greater than, you shade everything over on this side. Okay, that is it for this video. Thank you very much for watching. Tune into the channel for more videos soon.